Can you believe it? A factory that can swallow over 10,000 tons of steel and rise from nothing in less than 24 months. But that's only the surface. Right now, inside the semi-factory of Tesla, massive 4,680 battery packs are being assembled to deliver up to 1.2 megawatts of charging power. Enough to power an entire neighborhood, yet compressed into a single truck. And Tesla isn't stopping there. They're making an extreme bet: 50,000 semi-trucks per year. So what is really happening inside this factory? Why do the production lines here seem to fly? And why are traditional trucking giants holding their breath watching it? Let's step inside, right now. The first thing that quietly breaks your expectations isn't on the factory floor. It's above your head. Inside this new Tesla semi-factory, Tesla has turned the ceiling into a fully active production layer. Overhead carriers move entire vehicle modules weighing over 10,000 pounds, not just transporting them, but positioning them with precision down to plus or minus 0.5 millimeters. That level of accuracy doesn't just look impressive, it eliminates entire categories of industrial inefficiency. No forklifts, no cranes, no manual repositioning delays, which in traditional plants can account for up to 15% of total assembly time. But the real breakthrough is spatial. Traditional factories are trapped in two dimensions, where every process competes for limited floor space. Tesla adds a third dimension, unlocking a 30 to 40% reduction in required factory footprint for the same production output. That directly lowers capital cost per unit capacity, one of the hardest economic levers to optimize in automotive manufacturing. Then comes workflow efficiency. With modules suspended, workers and robots gain full 360-degree access, 6 directions simultaneously. No waiting to rotate parts, no blocked access. This alone boosts station-level productivity by around 25%, cutting assembly time per station by roughly 20 to 25% without increasing labor speed, just by eliminating idle time. And most critically, resilience. If one station fails, modules don't stop, they reroute. The system dynamically bypasses bottlenecks, maintaining continuous flow. That's how Tesla targets over 90% OEE. While most traditional automotive plants operate in the 75 to 85% range due to stoppages and linear dependencies. So the question becomes unavoidable. If your production line can move around problems instead of stopping for them, is it even a line anymore? Now as you move deeper inside, something even more radical appears, and it's almost invisible. For over a century, vehicles have been built in a straight line. One step follows another. One delay stops everything. Tesla walks away from that entirely. Instead, this factory operates on a modular, parallel architecture, an evolution of what many describe as the unboxed process. The cabin, chassis, drivetrain, and battery systems are built simultaneously in separate zones, only converging at the final marriage point. This changes the math of production. Work no longer queues behind previous steps. Multiple teams operate at once. Throughput increases without extending physical line length. In traditional systems, scaling means making the line longer or faster, both capital-intensive and operationally fragile. Here, scaling means adding parallel modules. That's why Tesla can target tens of thousands of units annually, with long-term ambitions of around 50,000 heavy-duty trucks per year, without hitting the physical constraints that limit manufacturers like Daimler Truck or Volvo Trucks. So the deeper question emerges. If production becomes parallel instead of sequential, what is the real limit of manufacturing speed? As you continue forward, you reach what used to be Tesla's biggest constraint: battery supply. For years, the delay of the Semi wasn't design, it was energy storage. That bottleneck is now structurally removed. By producing 4,680 battery cells directly at Gigafactory, Nevada, and feeding them into the Semi line in near real time, Tesla eliminates external dependency. More importantly, it uses dry electrode technology, a process that reduces energy consumption and cuts up to 50% of equipment investment and 70% of factory footprint in battery production. The impact is measurable. Higher throughput enables large-scale truck production. Lower cost per kilowatt-hour makes heavy-duty EVs economically viable at scale. For a truck with an estimated 800 to 1,000 kilowatt-hour battery pack, this is the difference between a niche product and a commercially dominant platform. And Tesla doesn't just install batteries, it builds the vehicle around them. The Semi uses 3 battery packs arranged low between the axles, lowering the center of gravity by roughly 20% compared to diesel trucks. That significantly reduces rollover risk, critical when jackknifing accounts for over 10% of heavy truck accidents. As you approach the end of the line, Tesla adds something most manufacturers avoid: extreme validation. Every semi is tested under megawatt-level charging, up to approximately 1.2 megawatts. This is not theoretical, it's real-world stress. At that power level, thermal management becomes the central challenge. Heat, connector durability, system stability, everything is pushed to its limit. Tesla validates every truck under these conditions before delivery. The results are operationally critical. The semi can charge from roughly 5% to 70% in about 30 minutes, perfectly aligned with mandatory driver rest periods after long-haul driving cycles. That alone makes electric trucking viable without disrupting logistics schedules. And thanks to regenerative braking, up to 80% of braking force is handled electrically, extending brake life by 2 to 3 times compared to traditional trucks. Because in this industry, downtime isn't just inconvenient, it's expensive. Operators can lose thousands of dollars per day per truck. Tesla isn't asking, does it work? It's asking, can it survive the worst-case scenario before it leaves the factory? Now step outside for a moment. Because the next breakthrough doesn't sit inside a building. The Semi-Factory and Gigafactory Nevada operate as one continuous system, not for convenience, but to eliminate time. Battery cells, stamped metal, injection-molded components, they aren't shipped, they flow. Tesla replaces truck-based logistics with direct transport systems, removing warehouses, inventory buffers, and transport delays entirely. In traditional manufacturing, parts can sit idle for days or even weeks, whereas here the goal is to achieve near-zero delay, where components move directly from production to transfer and immediately into assembly without interruption. This eliminates non-value-added time, periods where nothing is built, yet costs continue to accumulate. The result is profound. 2 factories functioning as a single machine. Moving back inside, you notice the robots, but they're not what you'd expect. Traditional automotive robots are rigid, one task, forever. Tesla shifts toward adaptive systems, robots that can change tools, switch roles, and evolve with the product. This flexibility matters more than it seems. Vehicle designs change constantly. In most factories, that means months of expensive retooling. Here, robots are reprogrammed instead of replaced. Production lines adapt without full redesigns. Future upgrades are integrated faster and at lower cost. This transforms the factory from a static asset into a programmable system. When you step back and look at everything together, the 3D production system, parallel assembly, real-time supply integration, in-house battery production, megawatt validation, adaptive robotics, and iterative factory design, you realize something fundamental. This isn't just a better factory. It's a system designed to eliminate time, collapse cost, and scale faster than anything in heavy industry today. And that leaves one final question hanging in the air. When a system like this scales globally, what happens to an entire industry built on slower, more rigid, and more expensive rules? So, how is a Tesla Semi actually built inside this factory? To understand the Tesla Semi, you have to forget everything Henry Ford taught the industry about the assembly line. Because Tesla's factory isn't a line, it's a 3D system engineered to compress time, space, and cost. Stage 1, cabin, starting with a complete module. The process doesn't begin with a bare frame crawling down a conveyor belt like in legacy factories. Instead, the Semi's cabin is assembled early as a nearly complete module. Structurally, this includes the core frame, mounting points, and initial systems integration. By doing this up front, Tesla removes one of the most complex and delay-prone stages from the main assembly flow. But here's the twist. The moment the cabin is ready, it doesn't stay on the ground. It gets lifted into an overhead carrier system. That single decision fundamentally changes factory dynamics. In traditional plants, large structures clog floor space, forcing everything else to root around them. Here, Tesla separates complexity vertically, not horizontally. The result is measurable: fewer bottlenecks, smoother flow, and a reduction in idle time between stations. And that leads directly to the system that makes all of this possible. Stage 2. The flying production line, a 3D logistics system. Look up, and you'll see the real backbone of the factory. Suspended carriers move massive assemblies, some exceeding 10,000 pounds over 4,500 kilograms, through a continuous loop above the factory floor. But this isn't just transport. These carriers position each module with a precision of around plus or minus 0.5 millimeters, eliminating the need for forklifts, cranes, or manual alignment tools. Now consider what that means in practice. In a conventional truck factory, repositioning a heavy component can take several minutes and multiple operators. Here, it happens automatically, at speeds of roughly 1 to 2 meters per second. That alone can double transfer efficiency between stations. More importantly, this system unlocks access. Workers and robots can approach the same component from 6 directions simultaneously: top, bottom, sides, front, and rear. Tesla estimates this reduces assembly time per station by roughly 20 to 25%, not because people are working faster, but because they're no longer waiting. And then comes the most underrated advantage: resilience. If one station goes down, the system doesn't stop. It reroutes. Modules can bypass the issue or shift to a parallel line, maintaining overall equipment effectiveness, OEE, close to or above 90%, a level most automotive plants struggle to sustain. But moving parts efficiently is only half the story. The real question is, what are these parts actually becoming? Stage 3, battery marriage, the structural heart of the truck. This is where the identity of the semi is defined. At a dedicated station, 3 massive battery packs are installed directly into the chassis. Unlike passenger EVs, where battery packs are flat skateboards, the Semi uses cube-like packs designed for maximum energy density within a constrained volume. Each truck integrates 3 packs operating in parallel. Combined, they are estimated to deliver enough energy for up to 500 miles, around 800 kilometers of range in the long-range variant. That's not just a spec, it's a design constraint that shapes everything else. The installation process is precise. High-torque tools secure the packs with exact force calibration, ensuring structural integrity under extreme loads. And because the batteries are so heavy, their placement directly affects weight distribution, stability, and handling. This is the key insight. The battery is not just a power source. It is the architecture. Everything, from frame geometry to suspension tuning, is built around it. And once the energy core is locked in, the rest of the machine begins to take shape. Stage 4, modular assembly, building in parallel, not sequence. Instead of adding thousands of small parts one by one, Tesla assembles large subsystems independently. Drive axles, steering systems, pneumatic components, and structural elements are built as complete modules and then integrated. This reduces the total number of assembly steps dramatically. In traditional truck manufacturing, you might see hundreds of sequential operations. Here, many of those steps happen simultaneously in parallel zones. The impact is clear. Fewer steps mean fewer chances for error, faster cycle times, and easier automation. It also makes scaling more efficient. Rather than extending a single line, Tesla can replicate module stations to increase output. One of the reasons the factory is targeting tens of thousands of units per year, eventually aiming for around 50,000 trucks annually. And as the physical structure nears completion, attention shifts from building to durability. Stage 5, coating and finishing, built for continuous load. Unlike passenger vehicles, trucks don't get breaks. They operate under constant stress, long distances, and harsh conditions. That's why the coating stage is not just cosmetic, it's functional. Each Semi is treated with corrosion-resistant coatings designed to withstand years of heavy-duty use. The materials and processes are closer to industrial equipment standards than consumer vehicles. This stage ensures that the truck can maintain structural integrity over hundreds of thousands of miles. Because in logistics, downtime is not an inconvenience, it's a direct financial loss. And before any vehicle leaves the line, it faces one final test. Stage 6, light tunnel, precision quality control. At the end of the assembly line, every truck passes through a high-intensity inspection system known as the light tunnel. Bright, controlled lighting exposes even the smallest surface imperfections, defects that might be invisible under normal conditions. But this isn't just about aesthetics, it's about consistency. At scale, maintaining uniform quality is one of the hardest challenges in manufacturing. This system acts as both a filter and a feedback loop, catching issues before delivery and feeding data back into the production system. It's also symbolic. After moving through a highly automated, high-speed process, this is the moment where everything is verified. And then, the product reveals its true purpose, not in the factory, but on the road. Stage 7, driving experience, where manufacturing meets reality. The way the Semi is built directly affects how it drives. With electric motors delivering instant torque, the truck responds immediately. No gear shifts, no lag. Even when hauling up to 40,000 pounds, about 18,000 kilograms, acceleration remains smooth and controlled. Energy efficiency is another critical metric. Real-world estimates place consumption at around 1.7 to 1.8 kilowatt-hours per mile, significantly lower operating cost compared to diesel trucks on a per-mile basis. Regenerative braking not only recovers energy but reduces wear on mechanical brakes, extending maintenance intervals. Combined with fewer moving parts overall, this leads to higher uptime, a crucial factor for fleet operators. The cabin itself is quieter, reducing driver fatigue over long hauls. The central seating position, paired with up to 10 exterior cameras, improves visibility and minimizes blind spots, one of the leading causes of trucking accidents. And perhaps most importantly, the system simplifies operation. No gear shifting, no engine braking management. That reduces training time and lowers the risk of human error. What you've just seen is not a traditional factory flow. It's a system built around speed, flexibility, and scale. By combining 3D logistics, modular assembly, and integrated battery architecture, Tesla has created something fundamentally different. This is Terrafab, a $25 billion factory that produces absolutely nothing you can touch. No steel, no components, no physical goods. The only thing born here is pure artificial intelligence. Tesla is betting its entire future on shattering the dominance of the world's chip giants. Why take such a massive risk? The answer lies right inside these doors. Sector 1, Raw Material and Silicon Entry. As the doors to the first sector open, the first thing that hits you isn't sound, it's an eerie silence. We are entering the sanctuary of 9N, where silicon reaches a purity of 99.9999999%. Let me help you visualize that. If this silicon wafer were a road stretching from New York to Los Angeles, a single speck of dust would only be allowed to be the size of a grain of sand. Why is Tesla obsessed with this purity? Because at the 2-nanometer process, we are no longer working with mechanics. We are dancing with individual atoms. At this scale, a stray organic molecule, a dead skin cell or a microscopic fiber, becomes a giant meteor crashing into the circuitry. Tesla doesn't just buy 300mm wafers from suppliers like an ordinary customer. They are reaching deep into the supply chain, controlling how silicon atoms are arranged from the very start. Why? Because if the substrate isn't perfect, every effort thereafter is meaningless. You cannot build a crystal palace on a cracked foundation. At Terrafab, perfection isn't a distant goal. It is the only passport that grants you entry into the 2-nanometer world. Sector 2, the EUV Cathedral. Crossing the preparation area, you enter the clean room, where hospital sterility standards become obsolete. This is the domain of the ASML TWINSCAN XC High-NA machines. Look at them. Each machine is a marvel worth over $200 million, more expensive than a luxury private jet. And it is the only thing on the planet capable of printing Tesla's future. Extreme ultraviolet light isn't just normal light. It is a form of energy so strange and fragile that air itself can swallow it. Therefore, the entire lithography process must occur in a vacuum as absolute as deep space. But here is the real turning point. Gate-all-around transistors. Forget the old architecture. With GAA, Tesla is crafting electromagnetic valves sealed on all sides. If the old transistors were a leaking faucet, GAA is a hermetically sealed system. Why does Tesla crave this? Because Terrafab is projected to consume 2 gigawatts of power, enough energy to light up an entire city. In a game of extinction-level scale, saving 30% of power via 2-nanometer chips isn't just a line on a financial report. It is the line between a sustainable autonomous empire and a power-hungry monster that collapses under its own weight. Sector 3, AI5 and Dojo. Deep inside the design core, you see Elon Musk's true philosophy. The best part is no part. While Intel or Nvidia must design chips to run Excel, play games, and process graphics simultaneously, a jack of all trades, master of none, Tesla does the exact opposite. Welcome to the kingdom of the AI5 chip and Dojo D1. These beasts weren't born for versatility. They were born for one thing: performing matrix multiplications at the speed of light. Tesla has aggressively stripped away decades of junk code and legacy architectures that slow down AI inference. The result? A brain that is lean, cold, and hyper-efficient. If an Nvidia chip is a Swiss Army knife, Tesla's AI5 is a samurai sword, single-edged, but sharp enough to slice through any data barrier. This isn't just Apple-style vertical integration. This is hyper-integration. Tesla is hand-casting the soul for millions of robotaxis and billions of Optimus robots. They don't buy intelligence, they manufacture it right here in Austin. Sector 4, 3D Fabric. Leaving the lithography zone, we enter a space where chips no longer exist as lonely islands. Welcome to the era of chiplets and 3D fabric technology. Why are we here? Because Moore's law is dying, and trying to cram more transistors onto a flat plane has hit physical limits. Tesla's answer: stacking. Imagine the AI processors and memory layers no longer sitting side by side on a circuit board, connected by slow, country roads. At Terrafab, they are bonded directly on top of each other, creating a high-speed elevator for data. With internal bandwidth reaching a staggering 36 to 50 terabytes per second, Tesla has officially killed the bottleneck. To put it simply, you could transfer the entire global Netflix library between chip cores in less than a blink. This isn't just an upgrade, it's a structural revolution. While legacy systems waste most of their time waiting for data to move from memory to the brain, at Terrafab, data is instantaneous. Sector 5, the AI training pipeline. If you are looking for an exit for physical products at Terrafab, you will be disappointed. This factory doesn't ship anything you can hold. Its final product is invisible yet all-powerful: evolution. Here, Tesla operates a perpetual loop. Every week, the system consumes roughly 70,000 GPU hours to digest billions of video frames from the real world. The result? Every passing week, the FSD software becomes one level smarter. It doesn't just learn to drive, it learns to understand the world. The most important metric here isn't horsepower, it's latency. Tesla has successfully slashed response latency by half. In the world of self-driving, 10 milliseconds isn't just a spec, it's the line between life and death. Terrafab doesn't sell chips, it sells reflexes that far exceed human capability. Sector 6, networking. To keep hundreds of thousands of GPUs from becoming a chaotic mob, they need a central nervous system. That is where NVIDIA Spectrum X and Tesla's custom InfiniBand protocols come in. There is a harsh rule in computing called Amdahl's law. As you add more processors, the incremental efficiency decreases due to communication overhead. Tesla is defying this law with a network efficiency of up to 95%. Compare this: typical data centers waste up to 40% of their energy just letting chips talk and wait for data. At Terrafab, that waste is nearly eliminated. Hundreds of thousands of cores operate in perfect sync, like a single entity, a massive brain spanning rows of racks. This isn't a computer network, it's a digital nervous system optimized for one purpose: the creation of intelligence. Sector 7, thermodynamics. The deeper we go, the roar of the cooling systems becomes more intense. This is where you realize the greatest challenge to AI isn't algorithms, it's thermodynamics. Every second, Terrafab consumes power equivalent to a small city, about 2 gigawatts. Without a solution, this heat would melt everything. Tesla has scrapped outdated fans and replaced them with liquid-to-chip cooling. Coolant is piped directly against the silicon surface to suck away every joule of heat the moment it's generated. But Tesla doesn't stop there. They apply circular economics to heat. 13 million gallons of water are recycled daily, and the waste heat from the supercomputers isn't vented away. It is being researched to heat buildings or provide thermal energy for steel stamping at the nearby Gigafactory. Terrafab is a biomechanical entity that utilizes every scrap of energy to survive. Sector 8, the final product. Why does Tesla need to own this entire massive supply chain? The answer is Optimus. For a humanoid robot to replace manual labor, it must be cheap. You cannot put a $40,000 brain into a machine you intend to sell for $20,000. Terrafab is the solution. By manufacturing chips at a scale of millions, Tesla can crush the cost of an AI brain from impossible down to a few dollars. Terrafab is the mother of every future Tesla product. From the steering wheel-less cybercab to armies of Optimus robots, all are born from algorithms refined here. Tesla isn't just building a factory, they are building the machine that builds the machines. How valuable is the product that the Terrafab factory actually creates? The true product of the Terrafab is not just silicon, but the industrialization of intelligence. To understand the significance of this output, one must look at the AI5 chip, which acts as the physiological heart for the next generation of Tesla's autonomy. In the world of high-end computing, most processors are designed to be general purpose, balancing graphics, rendering with complex mathematical operations. However, Tesla has abandoned this jack-of-all-trades philosophy. By utilizing a cutting-edge 3-nanometer process for initial runs and a 2-nanometer process for volume production, the AI5 delivers approximately 8 times the compute power and 5 times the bandwidth of its predecessor, AI4. It is built as a specialized samurai sword that ignores traditional graphics tasks to focus exclusively on matrix multiplications. This singular focus allows a single AI5 SoC to rival the inference performance of an NVIDIA H100, while a dual-chip configuration matches the NVIDIA Blackwell architecture. Crucially, it does so while operating at a mere fraction of the 700-watt TDP typical of high-end GPUs. This extreme efficiency is the only way a vehicle like the Cybercab or a robot like the Optimus Gen 3 can process massive streams of visual data, reaching 2,500 TOPS of performance, without draining its battery or requiring a massive liquid-cooled server rack on board. As we look deeper into the factory's pipeline, the roadmap extends into the AI6 and AI6.5 series, which represent Tesla's push to the absolute physical limits of semiconductor technology. The AI6 is engineered to double the performance of AI5 by integrating LPDDR6 memory and a 2-nanometer gate-all-around process, ensuring that data moves as fast as the processor can think. The most strategic revelation, however, is the AI6.5, produced in collaboration with Samsung and TSMC. This is the first chip designed specifically to allow humanoid robots to operate in a 24/7 industrial cycle, by moving to a full 2-nanometer process. Tesla achieves a level of thermal efficiency where the Optimus robot can perform high-intensity labor without the risk of overheating. This creates a functional bridge between digital AI that lives in a cloud and physical AI that can safely and tirelessly inhabit our physical world, supported by a production capacity aimed at 40,000 wafers per month. Parallel to these mobile brains is the production of the Dojo 3 training tiles. These are the massive, invisible products of the Terrafab that reside in supercomputer clusters rather than inside cars. Dojo 3 is the infrastructure that allows Tesla to reach the exaflop scale, the ability to perform a quintillion calculations per second. Each Dojo D1 chip already packs 354 independent processors and 440 megabytes of SRAM. But Dojo 3 scales this exponentially. By adopting a system-on-wafer design, Tesla has effectively eliminated the latency bottleneck that plagues traditional data centers, reducing energy per transmitted byte by up to 38%. Instead of data crawling through slow copper wires between individual chips, it flows instantaneously at bandwidths reaching 36 to 50 terabytes per second across a single, continuous wafer. This allows Tesla to train its FSD models, digesting billions of miles of real-world video in a matter of hours, creating a feedback loop of evolution that no competitor can keep pace with. The most profound value of these products, however, lies in their impact on Tesla's profit margins and global accessibility. Currently, the industry is beholden to a silicon tax where a single NVIDIA H100 or B200 can cost between $30,000 and $45,000. By controlling the entire manufacturing stack within the $25 billion Terrafab, Tesla brings the internal cost of these same units down to a few hundred or $1,000. This vertical integration is the secret sauce that transforms the robotaxi and Optimus from luxury prototypes into affordable consumer products. When the brain of a robot costs $500 instead of $50,000, the path to a $20,000 humanoid worker becomes a mathematical certainty rather than a marketing dream. Finally, the Terrafab's influence extends beyond our atmosphere through space-grade AI. In collaboration with SpaceX, the factory produces radiation-hardened chips capable of surviving the harsh environment of orbit and deep space. These chips turn the Starlink satellite constellation into a giant, orbiting supercomputer, with prototype 100-kilowatt AI mini-sats designed to process Earth observation data or interplanetary communications on the fly. Whether it is a car navigating a busy street in Austin, a robot working in a factory, or a satellite orbiting Mars, the products of the Terrafab represent a unified nervous system for a multiplanetary civilization. Tesla is no longer just a car company. It has become an industrial refinery for the fundamental currency of the 21st century, autonomous intelligence.